Hello everyone. In this video I would like to show you how to use the particle feature of OpenHydroQual to model settling in a very simple basically column. Basically this is just an instructional video, so it's the case that I'm presenting you is very simple, but you can use the same concepts and have basically model particle behavior in your systems that might be more complex. For example, if you want to, I don't know, model a clarifier as part of an activated sludge system, or if you want to model sediment transport, if you want to model the fate of suspended solids in, for example, a stormwater pond and things like that, you can use the same concepts. So basically what I will show you today is how to model a particle settling in a 1 meter column. So it's a very simple column. Its height is 1 meter and its cross-sectional area is, let's say, zero point 0.1 square meters. And what I will do is that I will assume that initially we have particles spread along the column at a concentration of 1 grams per cubic meters or 1 milligrams per liter. The way the particle feature that I'm going to use is basically it assumes discrete particle settling. So basically the settling velocity is constant, and that's what we're going to provide. And I'm gonna give let's say a 10 meters per day settling velocity. Uh, so um, so with that, so basically what I will do is that I will discretize my column into 10 layers, and then we'll do the essentially we'll solve the problem using a discretization with the size of each layer being zero point 0.1 meters or 10 centimeters. So let's get it started. I'm gonna go to okay, this is my OpenHydroQual window. So what I will do is that I'll first introduce my particle. Uh, and I have a reason for that. Basically, I want the reason why I'm doing that is that I will make it easier to essentially apply the initial condition when I create this array that represent my different layers. I can, at that time apply my initial condition that is going to be, 1 milligrams per liter in each of the cells essentially. So let's do that. So I'm gonna add this particle. Now keep in mind that a particle uh, is just like a constituent, right? So it goes under constituents. It's the same as constituent. You can basically essentially apply reactions to particles. For example, I don't know if you want to model the growth of biomass, but you want to also consider settling of biomass in a, let's say, activated sludge system. You can do it. You can have the particles, for example, reacting, undergoing quote unquote chemical or biological reactions with other constituents. So, for example, you may have dissolved organic carbon, which is going to be a constituent, which is going to be dissolved, um, and then you have particles, and somehow particles basically react with this dissolved organic matter. So as a result of having dissolved organic matter, they may grow. So anyways, this is my particle. I'm gonna keep the name the same. The only basically property that I'm gonna apply to the particle is this settling velocity, which, as I said, I'm gonna make it 1 meters per day. So I'm gonna make it one, and then the unit I'm gonna pick meters per day, right? So they are, I don't know, maybe really colloidal small particles, and their settling velocity is that low. Then so I had oops. I need to press enter after I change the value. Okay, so now it's 1 meters per day. And so now what I'm gonna do is that I'll add this plugin. So basically currently this process of settling is in or actually what I'm gonna do is that I'll use this feature called settling tank for settling, but you can model settling in many other components as well. I'm gonna explain more about that in a second. So what I'm gonna do is that I'll go to preferences, add plugin, and I will add this plugin called mass transfer. The mass transfer, it contains basically a component called basically clarifier element, or I'm sorry, settling element or something like that. So uh, now let me tell you one thing. You can apply. So basically, when I add this feature, I'm gonna get this reactor, and then I'm gonna get this component called settling element, and then also I'm gonna get this link, which is settling element interface. So this is supposed to serve as the interface between two settling elements when settling happen across. Now, uh, the thing is that you can do particle transport in many other elements as well. We don't have to use this settling element. The only thing is that in order for particle transport to be modeled, or settling to be modeled in particular, not particle transport but settling, the components need to have a few things. They should have a bottom elevation. So not all components in OpenHydroQual necessarily have this property called bottom elevation. Uh, and the way bottom elevation is used is that the settling happens from a block with a higher bottom elevation to a lower one. Now, if you don't have, then basically settling will not be accounted for in your model. You may get some warnings when you run the simulation, but your simulation will be done. But for those blocks, settling actually will not be essentially in effect. The other thing that we need to have is that we need to have any link that we use that we want settling to happen through. It should have an area. Okay, so basically, not all links not all links have a property called area. So if you have a link that doesn't have area, you're gonna a warning. The model will still run, but settling will not happen through those links. So okay, so keep in mind that we have now a particle called particle 1. Okay, this is the name. Now you can go and change the name, and that may make things easier. Um, but I'm gonna stick with particle 1. You can have multiple particles in your system with different properties, maybe undergoing different kind of reactions and so forth. But I'm gonna keep this simple. So at this time, what I want to do is that I want to create an array that will basically constitute my column. Okay, so basically I go to add objects, I click on create 2D array, and then what I will do is that for the block type I choose settling element, and for the link type I choose settling element interface. And then what I will do is that I only have one grid cell in horizontal direction, and then I have 10 in vertical direction. Then so I go to next, and then now I have to specify the properties of my block. So what I will do is basically now here I can assign, actually let me expand this a little bit so you can see the name of the properties completely. So basically for particle concentration, as I said, I'm gonna go with 1 milligrams per liter, which is 1 gram per cubic meters. We don't have an external mass flow time series, but if you have basically some particles coming in laterally into the column for some reason, you can actually provide the time series here. Then we don't have an so I'm gonna leave these height, width, x, y. These are all just graphical properties, how you want those blocks to be shown on your GUI. Then so basically we don't have an external source, so I'm going to leave that empty. For the bottom elevation, what we're going to do is that we're going to start from the top cell, and then we're going to go down. So I'd say I indicate an elevation of 0.9 meters for the bottom elevation of the top cell. And then what I say here is this is if you look, it's vertical increment. So I make vertical increment minus 0.1. So basically, as these blocks are generated, the elevation goes down by 0.1. And then the initial storage. So if you remember, the cross-sectional area of our column was 0.1 square meters, and then the height of each of the elements is 0.1 meter. So the volume is going to be 0.01 cubic meters, and that's going to be the initial storage, which is going to remain unchanged during the simulation because no flow is coming in or going out of these elements. Now, if you have some inflow and outflow, for example, you have a clarifier for you know, removing, let's say, solids from a wastewater system. In a wastewater system, then you have some flow, but we have to make sure that the flow in and flow out into each of the elements are the same, so that the storage does not change. Then, so that's all we need for the block. Now I'm going to go to the next one. The flow rate, we don't have a flow rate. The interface area, I'm going to enter the interface area, which is going to be 0.1 square meter. So this is the interface area of our basically interface, our links between each two basically settling elements. And this is basically, it's the variable. If you look at the JSON files for you know, these you know, the plugin, it's called mass transfer plugin, you will see that the interface, the name of the variable is actually area. So this is going to be used to calculate the flux. And this is pretty much it. We don't have any link in, you know, basically essentially we only have link in y direction, but whatever number you enter for the xx, it's going to be automatically copied to the y direction too. And that's pretty much it. This is all we have, and I'm going to just click on generate, and now we have the column. So we have 10 elements. I can check the properties to make sure everything is produced correctly. So we have the concentration is 1 gram per cubic meter. That's our initial concentration. The names, you know, it's just assigned automatically. We have the bottom elevation, which is 0.9, and then if I go to the next one, it's going to be 0.8. The bottom one is going to be 0, and the initial storage is 0.01. We can also check the variables for the links. Of course, we have a flow rate of 0, an interface area of 0.1. So that's it. Now I'm going to save my model, and then I'll run it. So let's just go here and save it. I'm going to save it as I'm going to call it settling column. That's it. So so now we can run it. Let's see what happens. So I'm gonna just run the model. Here it is. We didn't get any warnings, and the simulation is done. Now we can check the results. So let's do, I don't know, for example, I can look at the concentration at the top. As you can see, the concentration actually drops exponentially. By the way, the settling velocity that I entered was actually 1 meters per day. I think I initially mentioned 10 meters per day. I'm gonna try that too. So then we can look at, let's say, concentration here. Takes a little longer for it to drop. Let's just compare. So I'm gonna copy this, maybe paste it here. So here I have basically the concentration at the top layer in the middle of the column. Let's also look at the bottom of the column. So this is the concentration at the bottom of the column, which is increasing. I can copy this and maybe paste it on this one. So this is how the concentration varies at different locations. Now what I want to do is, let's do one more step. So what I'm going to do is that I'll add another particle, this time with a higher with a larger settling velocity. Now the thing is that since I have already created my array, I have to go and apply my initial condition to every single of these, which is going to take some time. So to avoid that, what I will do is that I'll just assume that these particles with a higher settling velocity only present at my top 2 layers. Okay, so basically I'm going to click on this one. So now I have two particles. For this one, I'm going to say the settling velocity is 10 meters per day. Okay, so it's 10 meters per day. And what I will do is that now I have this particle 2. The second particle is called particle 2. And I'm going to say the concentration again. The initial concentration, the top column is 1 gram per cubic meters. The second one is also, the second from the top is also 1 grams per cubic meters. And everything else is fine. So let me just save my model and then I'll run it again. Now let's look at the results for particle 2. So here I can look at the concentration of particle 2. As you can see, it drops really quickly. Let's also look at the mid column. So particle 2 concentration, the mid column looks like this. So the wave comes and then go. Let's copy this one here. And you'll get some numerical dispersion, even though we didn't put dispersion in the model, but people who are familiar with solving basically one-dimensional advection equations, they know that we get some numerical dispersion, which can be reduced if we increase the basically refinement of our discretization, basically by having more columns, more segments, more elements. And basically we can look at the bottom, and this is what we have. Let's paste that, and here it is. Thank you for watching, and look for my future videos.